So it doesn't seem like there's very many help items that directly tell you how to use or set up generalized displacements using SAP2000. So this short video will show you how to define a generalized displacement so you can measure, say, the strain of a truss member. So for this example, we have our simply supported truss. 2 point loads are being applied at the bottom chord. And we want to take a look at what is the strain within the member that goes from node 5 to node 6 on this structure. So to do that, we could go ahead and hit run. Okay, and when we hit run, we're gonna only be using our dead load case. We'll run now, and we'll get our deflection. And so we could go ahead and take a look at this node, right click on it, and it'll tell us what our displacement or our translation in the x direction is at object 6.00245. We could record that and go ahead and take a look at what our displacement is at our other node at element number 5. You can see our displacement is 0.00477, and we can go ahead and calculate the change in length and deal with it in that way. Or we can use generalized displacement. So without having to unlock the structure, we can go to define generalized displacements, and we'll simply add a new generalized displacement. And here we're going to call this member 5/6, and here I just want to see what is the delta or the change in length, and I'm just going to isolate it to along the x direction. Okay, and so this is a translation that we're looking at. I want to set this up so that I have a tension as a positive displacement or change in length and compression as negative. So at node number 5 here, that I want a positive addition to my translation if the displacement is negative, opposite of the x direction. So here at joint 5, I want my U1, which is consistent with the global x direction, to be a -1. So it's going to take whatever the displacement is, multiply it by -1, okay, and then add it to any other of the other items that have a non-zero value. Okay, so the other one that I care about is node number 6, which is at the opposite end of that member. Since it's at the opposite end of the member, here, if the translation of this object in the positive x direction occurs, that means that this member is going into tension, which is what I want. So instead of it being -1, I'm going to say that this is 1. Okay, and so I'll add that to the case. So what will happen is it'll take any of these displacements and or rotations, the actual output data, multiply it by the corresponding value at each joint. In this case we have 2 joints, and then add all of them together. Okay, so it's going to be displacement in the x times -1 at joint 5, displacement at joint 6 in the positive x direction times 1, and then it's going to add those 2 together. That's what this means. Okay, so I'll say OK, OK, and so now I'm going to go ahead and go to display, show my tables. Okay, and then within this I'm going to go to analysis results, joint output, displacements, and you can see there's a separate table, joint displacements generalized. Okay, I'm going to select OK, and what comes up is this generalized displacement. So this is the displacement we just defined, member 5/6, delta x translation. This is the dead load case, and here we have the change in length of that member in inches is 0.002319. Okay, so 002319 is what we had, and so that should be the difference, 0.0023, in displacement between there and there. Okay, so this member got shorter. We can take a look at that again. Let me change this display. I change it to color printer. Okay, then we can see it a little easier. So here we can see U1 is 0.0025 at node 6, so that's translating to the right. And then we have 0.0048, okay, which is about 0.0023 more here than it is here, meaning this is going into compression. So again, if we display, show tables, okay, and so our generalized displacement is negative 0.0023. Okay, so that's the total change in length. Okay, but maybe I don't care about the change in length. I just want to know what the strain is for this member. Okay, so I'm going to go ahead and define another generalized displacement. So I'm going to add a new displacement. This one I'm going to call, okay, member 5,6. And instead of delta x, I want it to be strain in the x direction. Okay, so starting at member 5, again, a negative displacement. Positive displacement there is compression, so negative 1. But the total member length here the total member length is 12 feet. So I need to divide it by 12 feet. Output's going to be in inches, so I'm going to divide that by 144 because that's the total member length. Okay, and that's going to do that calculation for us. Go ahead and add that. At node number 6, okay, I just want to change my sign so that a positive x direction displacement is consistent with positive being tension in that member. So I'm just changing the sign there. It's also 1 divided by 144 is the same value there. So it does that calculation for us. We'll add that. So again, it's going to multiply the x displacement at joint 5 times minus 1 over 144. And it's going to add to that the x displacement at joint 6 times 1 over 144. Combine that together and that'll give us our value of strain. Okay. We'll say okay, okay. So we're going to display, show tables. Okay, the same options are there since we haven't changed anything. And so now it's showing the change in length, which is that 0.0023. Okay, and so if we take that 0.0023 and we divide it by the length of the member, the length from here to here is 12 feet or 144 inches. 0.0023 divided by 144 should give us 4 zeros and 1 6. Okay, so we can go ahead and confirm that. If I take 0.0023 and I divide it by 144, my calculator, I get basically this value here. Okay, so that's the strain. Now, and we can see that it's 3 zeros, a fourth zero, and 6, so that's 16 microstrain. So instead of reading all these zeros, I just want the output to be in microstrain. So I can, again, go ahead and define a generalized displacement. Okay, I'm going to add a new displacement. Okay, and this one, I want it to be, again, member 5,6. Okay, and instead of strain x, I'm going to say microstrain in the x direction. Okay, and so this, again, number 5, I want it to be in the negative x direction, gives me a positive result for this calculation, but I want it to be in microstrain, so I'm going to take whatever my strain value is, multiply it by 1,000,000, okay, or whatever my displacement value, if I multiply that by 1,000,000, and then I divide it by the length of the member, which is 144 inches, then that'll be my change in strain based on the displacement of node number 5, but strain is actually the relative displacements between the two nodes at the end of the member. So again, x being positive, so I take 1,000,000 divided by 144, which would have been the same result. So that's positive. Add that to my case. So again, the displacement in the x direction for joint 5 times 1,000,000 to get it to microstrain, divided by 144 to convert it to strain in the first place, plus the displacement at node 6 in the positive direction, divided by 144 to get it into strain, multiply it by 1,000,000 to get it into microstrain, and we should be good to go. So we're okay, say okay, and if we go ahead and go to our display, show tables, okay, and we again want our displacements, our generalized displacement table is what's going to be shown. And here what comes up is we have our change in length, our strain, and then now our microstrain is that 6 16 microstrain, it's minus, meaning it's in compression. So we've basically just moved the decimal place over. Okay, so that's what it's doing. It's just linearly adding or subtracting based on whatever coefficient you want to multiply your displacement and or translation by. Okay, so you can do any various combinations, calculate your rotation of members, anything you want. All right, I hope that helps. Took me a while to figure this out because there's no real help online, so I hope this helps other people who are in the same place.